Hi, my name is StefanoMezzini and I'm an undergraduate student at the University of Regina. I will be presenting on how we can use big data and a time-to-event approach to estimate large-scale changes in lake ice phenology. The first question I would like to address is why lake ice? Well, many lakes freeze periodically, and the loss of lake ice cover is a good indicator of climate change. Its loss also has significant impacts on many cultures and economies, including those of indigenous peoples, so it is not only important from a biological point of view, but also a societal one. And although many studies have been published on the loss of lake ice, most of them model a single time series at a time, which prevents them from estimating common or spatial trends between lakes, nor can they extend predictions past the range of the data. By modeling multiple time series at once, we can estimate the spatial patterns in the data, and also extrapolate for areas which have little or no data, while also providing a measure of uncertainty in the estimates. Finally, many commonly used methods such as linear models are not appropriate for nonlinear trends, and many of the assumptions in these methods are also violated, which means that these methods should not be used for estimating changes in lake ice phenology. We use the Global Lake and River Ice Phenology Database to estimate the hazard of freezing or thawing for a total of 563 lakes throughout the Northern Hemisphere. We fit a total of 4 models to estimate the daily hazard of freezing or thawing in North America and Eurasia since 1950. Including so many lakes in the models allowed us to estimate common trends between lakes and spatial trends, as well as use a longer time span than most of the individual time series in the record. However, since the sample of lakes was not random, their spatial distribution was not constant or uniform over the years. While this increased the uncertainty in some of the estimates, all possible steps were taken to account for differences in the trends between locations. Notice, for example, how northern and western Canada do not have any data after 1994. Still, our conclusions do not deviate substantially from those published in recent papers. To estimate the lake's daily hazard of freezing or thawing, we used hierarchical piecewise exponential additive models, which are an extension of GAMS with the Poisson likelihood. The figure below shows some of the freeze and thaw dates for Lake Suwa in Japan and Wascana Lake in Regina, Canada. The blue shaded area indicates when the lakes were frozen, while the orange shaded area indicates when the lakes were ice-free. Note that there is some variability between and within lakes, as well as a chance of not freezing at all, as in the case of Lake Suwa in 1971. The green baseline for Wascana Lake in 1974 indicates that the lake did freeze, but the date is unknown, so the event is interval censored. Unfortunately, the PAM-Tools package cannot currently handle interval censored data, but the observation was kept in the dataset anyway to inform the model that the lake froze. Of course, lakes can only thaw if they were previously frozen, so any years in which lakes did not freeze were excluded from the thaw datasets. To avoid discontinuity that occurs when converting dates to day of year, freeze dates were converted to the number of days after June 30th, while thaw dates were converted to the number of days after September 30th. The 4 models for freeze and thaw days for North America and Eurasia had the same structure. The log mean hazard of the event was estimated as the sum of multiple smooth functions. A smooth of the number of days after the reference date allowed the hazard to vary seasonally. A smooth of year allowed the average hazard to vary over the years, and a tensor interaction of these two terms allowed the seasonal term to vary over the years. Random effect smooths for t-end and year allowed the seasonal and yearly terms to vary slightly at the lake level, so that any remaining variance could be mopped up. A two-dimensional Duchamp-spline smooth allowed the hazard to vary spatially, so that the model could account for the effects of longitude and continentality. And finally, tensor interaction terms between the spatial term and the temporal terms allowed the seasonal and long-term trends to vary spatially as well. In order to keep the talk short, I will focus on North American models and their results, but please feel free to ask any questions regarding the Eurasian models as well. We can use these models to estimate the change in the average freeze and thaw dates as the days in which the events had an occurrence probability of 0.5. On average, North American lakes in 2010 froze approximately 33 days later than in 1950, and they thawed 10 days earlier. Since the hazards vary smoothly over the years, these models were able to adjust to the acceleration in ice loss post-1995. And while the 2010 estimates are more uncertain due to lower data availability, our results do not deviate substantially from those in recently published papers. We can see how these trends vary spatially by including space in our predictions. More northern and continental lakes tended to freeze earlier than southern and coastal ones. However, lakes in northern and western Canada have had a much greater shift than American lakes. This is particularly visible when we plot the difference between the expected freezing dates in 1950 and in 2010, and we filter to significant differences only, based on an 89% credible interval. Lakes in central Canada were estimated to have frozen 1 to 2 months later in 2010, while lakes in northwestern Canada were estimated to have frozen significantly later by 3 to 4 months, despite having greater uncertainty due to a lack of data after 1994. The thaw model shows a widespread shift to earlier thaw dates, except for lakes in the southeastern US, which appeared to be thawing later. This is easier to see when we filter to significant differences only. This time, it appears that the lack of data in the north and west may have had a greater impact, although there are still some areas with significant change. The presence of significant shifts towards both later and earlier thaw dates shows the importance of accounting for spatial patterns in lake ice phenology. Part of the uncertainty in the date estimates is likely due to the opportunistic nature of the sample. The underrepresentation of lakes in northern and rural areas may have also led to an underestimation in the loss of ice in lakes at higher latitudes. Similarly, the lack of lakes that only freeze occasionally or have stopped freezing may have resulted in an underestimation of the loss of lake ice in temperate regions. Of course, one solution to this problem would be more data, especially at higher latitudes. A second option would be to group the North American and Eurasian data into 2 models only for freeze and thaw dates, rather than 2 per continent, but this would greatly increase the computational cost. Another option would be to include additional predictors, such as lake altitude and daily air temperature. Lagged air temperature could also be used to account for exposure to sub-zero or above zero temperatures. Finally, wind strength and direction could also be used to account for wind disturbance. In conclusion, our models estimated strong and significant spatial temporal trends in the freeze and thaw dates of lakes, while also extrapolating for areas with little to no data. Although the uncertainty in some areas is higher than desirable, the models indicate very strong and accelerating changes after 1995 towards widespread later freezing and earlier thawing. The presence of opposing trends in the thaw model emphasizes the importance of accounting for spatial trends when estimating changes in lake ice phenology. I would like to thank all contributors to the Global Lake and River Ice Phenology Database, including Drs. Benson, Magnuson, and Federer. I would also like to thank Drs. Benson, Magnuson, and Sharma for maintaining the database. Finally, I would also like to thank the Faculty of Graduate Studies and Research and the NSERC Discovery Grants for funding. And with that, I thank you for your attention.